Welcome, everyone. We're really glad to be here to talk about product reliability for Google Maps. Again, I'm Joe Abrams, and I just killed my mic. And this is Micah Lerner. So this is kind of a look at what we'll be covering. We'll give a brief introduction about ourselves. I'll talk about the background and motivation for our work. Then Micah will walk us through our journey to user experience-focused SRE engagements. And then finally, I'll cover some of the learnings that we had along the way and some of the work we're going to be doing next. All right, so before we get started, this is us again. Micah, would you like to introduce yourself?
Sure. Hi, I'm Micah. I'm a tech lead on our team of 20 SREs spread across San Francisco and Sydney. Previously, I've had the opportunity to be a part of infrastructure and reliability-focused teams at Mapbox and Strava.
Thanks, Micah. And again, I'm Joe Abrams, team lead of Google Maps Site Reliability Engineering. And before this, I was causing, detecting, fixing outages for various products like Pandora, AWS, and Sony Crackle. I'll now share a little bit of background and motivation for our journey to product reliability. Our team is on call for a widely used consumer application, Google Maps. You've probably used it before. It's been around for almost 20 years. I actually looked that up on Wikipedia yesterday, and it's kind of hard to believe. And it boasts over 1 billion monthly active users. It's an incredibly feature-rich application capable of mapping, routing, searching for places, searching for businesses, and many other features. And as a result, we have challenges from running global services at a huge scale while maintaining high availability and low latency. Our apps are serving a global user base with a wide variety of operating systems and a very wide variety of device capabilities. So talking a little bit about the challenges we've had, over the years, we noticed that server reliability investments like global redundancy and graceful fault handling had really started to pay off. The number of SLO misses our team was paged for was dropping, and users were getting a pretty reliable experience. The classic server meltdown type outages that we've all probably experienced at one time or other were getting more and more rare. So we're very fortunate to be in that position, and I think just a testament to the maturity of the product and the hard work that's gone into it. When we analyzed our postmortems and incidents in a quest to make things even better for users, we noticed a trend start to form. Many of our remaining outages were things we weren't catching with traditional server alerts. As you can see in this chart, a majority of incidents were manually detected, which is obviously not ideal. These issues were more subtle, where servers were running well, but the user experience was not what users were expecting. In many of those cases, when we would do a debrief, it wasn't even clear how we would catch these incidents with our existing tools and our existing server monitoring. Next, I'll share some examples of the kinds of outages we were looking at. All right. So in this case, an end user who might have been at the 16th and Mission BART stop in San Francisco was trying to use Google Maps to get to Embarcadero, which is the BART station you might have taken today, you might have ended up at today. And then when they entered this into the app, this is what they got. Anyone see anything wrong here? I would not recommend taking that route, and I don't think it's really possible on BART. It's not what a user expects, and if I were a user, I'd be a little concerned just seeing that. So this outage was caused by a data update, and it was completely invisible in our server SLOs. Latency and availability looked totally normal. Because of a large number of transit lines we served, numerous failure modes, and numerous data sources, this was very difficult to catch with our existing tools. All right, here's another example. Here's a brief outage caused by an update to our iPhone client application. We have this innovative new feature called Immersive View that you can see there. And it lets you experience a place before you visit in 3D with a lot of really cool animation. Sometimes outages are caused by an interaction with a specific operating system version that slips into production. And that's kind of what happened here. Again, we didn't see this outage show up in our traditional SLOs or SLO alerts. Luckily, in this case, we actually did have some user-focused instrumentation, and we're able to detect it and mitigate it rapidly. But the issue that some users experienced was that they would click open and it wouldn't even open. And you can kind of see in that chart that for new versions, the successful opens rate was really low. All right, for 2 app versions, yellow and green. All right, for the final outage I will share was another outage we were previously unable to detect with server alerts. And in this case, someone, again, was in San Francisco, and they searched for coffee. And Google Maps told them, Google Maps can't find coffee. That's a little hard to believe for San Francisco, where I think you could pretty much just stumble into a coffee shop if you were blindfolded. So we weren't giving the user the right results in this case. And again, we didn't see in our SLOs. And you might think it'd be easy to add a service level alert for empty search responses, but it was surprisingly hard because there were many cases where having no results is actually expected and a valid response from our servers. And adding another alert for a very minor change affecting a small subset of users could be lost in the noise. We had another similar past incident where we saw an issue where users searched for a well-known mobile carrier and also got no results. And that one was caused by a code push. So when we analyzed these outages, along with others, to understand how we could prevent them or catch them faster, we identified 2 main gaps. First, our production alerting, which is great for telling us when a server is getting too hot, didn't capture the full user experience, as you could see in those examples. And second, given that many outages were caused by some sort of code change or release, we weren't always informing our code management systems when there was an automated alert. And that led us to a couple insights. To move the needle on catching issues earlier and minimizing impact, which is our job, our organization decided to change the way we approach reliability, shifting our focus towards user centricity. And then to support our product's rapid innovation, we worked to add more user centricity into our feedback loops, our delivery feedback loops. And next, Micah will share some details on our journey towards user centricity.
Great. Thanks, Joe. I'm now going to talk about how we address these issues via a pivot to user experience-focused engagements. There were 3 prongs to our strategy. First, we partnered with owners of core user experiences to align on feature criticality and the potential severity of outages. From there, we began building the technical implementation of signals that would allow us to directly measure the user experience, in some cases, harnessing existing work by our partner teams. Lastly, we integrated these signals in a system capable of preventing and detecting outages, which we call defense in depth. We use the phrase defense in depth because our multi-layered approach is capable of preventing and detecting outages, even those caused by a complex sequence of changes. So I'm now going to talk about engaging with product teams. So what we aim to understand is, as part of those conversations, is which features and their components were the most important. We often built on our existing relationships with developer teams with whom we co-defended server-side SLOs. Examples of questions we asked as part of this new type of engagement were, what qualifies as a must-win from the user's perspective? If a feature is broken, degraded, or has poor performance, will the user notice? What's the impact of failure? Do we lose revenue, or will users seek out alternative solutions to fulfill their needs? And lastly, what regressions are severe enough that the business will invest concrete resources, specifically incident management, to fix problems urgently. Next, we turned these discussions into concrete technical implementations. For several types of direct measurements, the signals were already developed by engineers on a product team, but the team wasn't using them yet for automated prevention and detection of outages. In other situations, these conversations led to developers investing in building out signals that could feed into our automated systems. Borrowing from our experience with the types of issues that we would be on call for with serving systems, we focused on three main types of measurements. First, availability, which captures whether a feature is working at all for a user. Second, latency, which measures the performance of a feature. While latency regressions are sometimes not as severe for users, based on previous research from Google, we know that even milliseconds of delay on critical features like search impact how people use the product. And last, data quality, which represents whether the information we return to a user is highly relevant and contains all of the results that will let them complete their journeys in Google Maps. Data quality is important because our partners in product teams have built experiences that surprise and delight users. While our infrastructure is capable of functioning in a degraded state to power a subset of functionality, we still want to know if we're not returning optional but important information. So the first measurement I'm going to talk about is availability, which captures whether users are able to achieve their goals. There are two primary ways we can measure user success. The first is determining whether a feature is working at all for a user. When a user clicks a button, does it take them to the expected destination? We built monitoring using a core dataset that developers add when implementing new features to log impressions and interactions on user interface components called visual elements. Teams would often implement these signals to understand whether users were engaging with an area of the product. For example, was a new feature increasing engagement with search results? The automated systems we built analyze this data to determine whether a sequence of user interface elements occur as expected. For example, if a user enters a search query, they should then see a list of search results. We feed these if this, then that assertions into our automated change supervision and production alerting systems, meaning that we can catch anomalies quickly. Beyond user interactions, we also have system health metrics like app crashes, which can also impact the availability of the user experience. Next, we focused on latency. One aspect of measuring the user experience is knowing how applications respond when the user performs actions like clicking on a button. Was the experience noticeably slow? If the responsiveness of the app is bad enough, it might be indistinguishable from the feature being broken. The graph on the right shows one type of signal that we use to assess performance, called traces. The image visualizes execution of code in Google Maps using an open source tool called Perfetto that is built into Android. Each color in the graph is associated with timing information on events like UI rendering. From this raw signal, we can calculate an alert on user-perceived latency. One added benefit of tracing is debuggability, meaning that we're able to dive deep on why performance has regressed. For example, is the code that actually draws the UI on screen slower? Did someone unintentionally add logic that runs on the main thread when it should run in a background thread? Has the networking stack changed to add new calls? Have existing ones gotten suddenly slower? These types of latency measurements are also closely associated with rendering. For example, are we dropping frames during an animation? The last main category of signal we ingest is data quality, which captures aspects of the information returned to users. Many user interfaces in the products we're responsible for are powered by a microservice architecture with downstream dependencies. To prevent a single downstream dependency from causing a major feature to break, we implement a technique called graceful degradation. Rather than failing the entirety of the request, we will return a subset of the information that we could have returned. Examples of this include displaying suboptimal search suggestions search results, or not showing features in the view of a point of interest in Google Maps. Data quality is slightly more nuanced than other user experience monitoring, where something is obviously broken for users. Instead, data quality regressions lead to a slow boil of less useful features, ultimately impacting business metrics like user engagement, adoption, and retention. All three of these user experience measurements flow into automated alerting systems that allow us to prevent and detect outages. To prevent outages, we focused on change supervision of three main change vectors. First, server rollouts, which involve deploying a new version of server code or configuration in the cloud. Second, application binary releases, which involve shipping a new version of a mobile application's code to an app marketplace. This change vector is particularly challenging. We can't roll back a released app if it contains a user impacting issue in the same way that we can a server in the cloud, heightening the importance of supervising this change vector. And lastly, feature ramps, where testing a new feature with X% of users can cause issues for a subpopulation. One insight we have is that change vector supervision is not enough. Occasionally, changes outside of our control have led to user impacting outages, but we still want to respond to the incident, triage, and ensure it is mitigated quickly. As a result, we also use the same user experience measurements in near real-time alerting systems to monitor beyond the rollout. To illustrate the importance of change vector supervision, here's a look at a past set of significant outages. In many cases, the outages were caused by some change on our end, like an application binary release, a feature ramp, or a server rollout. In a small number of cases not shown here, incidents were caused by networking infrastructure or an external factor that our product area has minimal control over. In those situations, we were able to quickly respond, triage, and escalate the underlying issue to resolve it. We're now going to dive a bit deeper into a case study that demonstrates how impactful these capabilities have been for our organization. Before, it was sometimes difficult to draw a direct connection between reliability work and business priorities. While we were able to defend server-side availability and latency SLOs, there was sometimes a circuitous route to user impact. For example, a server in the cloud could return a large number of errors, but the impact could be minimal due to factors like client retries, graceful feature degradation, and multiple levels of caching. Now, with direct measurements of the user experience, we've been able to easily understand the impact of an outage. The impact isn't our server in the cloud returned errors. It is, instead, those errors led to a significant increase in user perceived latency. This new form of understanding and talking about user impact has also empowered our team to drive reliability improvements that directly impact critical business metrics. For zero results, we were able to quantify the failure mode's impact to user engagement, adoption, and retention. Predictably, users attempting to search in Google Maps look for alternative options if the feature wasn't working. Before we implemented user experience signals and defense in depth for the search experience, there are occurring serious outages every year. Through our work to catch outages earlier, an effort we call shifting left, we've prevented these significant outages from escaping. Furthermore, we have a last line of defense in production alerts that page on-callers, meaning that we quickly respond to automated alerts rather than reports from our users. This shift has dramatically reduced our mean time to detection and resolution of outages. And with that, I'll hand it back to Joe.
All right, thanks, Micah. I'll now share some of the lessons we learned along the way and also discuss what's coming up next. So the zero search results outages that we've been talking about over and over were particularly challenging for us because we are a company known for its search, and we want it to be working very well. At first, when we added monitoring improvements, it actually led to the perception of more outages because we were able to catch some very small issues and that had subtle impact on our end users. So that was kind of a first learning. There was more outages initially. The second was that it was very costly to debug and fix a lot of the new kinds of outages we were finding because we'd have to drill very deep into the stack to figure out what was going on. All of these factors led us to kick off a Code Yellow, which is an internal event where we immediately form a temporary team from across different organizations to tackle an important reliability issue. A key pillar of this event was to invest in our change supervision tooling to be aware when users were getting unexpected search results. Shifting left reduces user impact as well as detection costs because it's very clear when something breaks and what most likely caused the problem. The focus on integrating into the delivery loop was a major aha moment for our exec sponsors and ourselves. It shifted the way we actually talk about reliability. And when we're proposing that a team does some reliability monitoring around a given feature, we often frame it around not just reliability, but improvements to delivery and velocity, which has been another learning. And that, of course, resonates quite well with our dev partners. We've found that we get a really good response when we talk about these investments using phrases like, let's apply the same protections we used in the Code Yellow, but for this new feature that you're building. So another learning we had was around getting buy-in from product owners. Adding product reliability monitoring is unfortunately not free and comes with certain costs. There's an initial investment in setting up this new kind of monitoring, and then, of course, learning. And like I talked about, the debugging takes a lot of training. Automated alerts based on user experiences can be expensive to debug and also sometimes turn out to be false positives, or some of the alerts you get turn out to be false positives. A significant portion of these costs are offset by velocity and reliability gains, of course. With more signals and automated checks in place, teams can move faster with more confidence when they're making changes that they will not be hurting the user experience. But one learning we had was to be really clear about the upfront costs with stakeholders and the changes that will happen so they're not surprised. And we found it's useful to minimize startup investment by introducing the concept in a pilot around a well-scoped feature set. So don't try to boil the ocean when you start out. Finally, I'll talk a little bit about our future work. User experience monitoring comes with its own unique challenges. Some issues are more difficult to root cause and mitigate, especially if they're contained in code that's been released to an app marketplace. We've continued to work on these tools to pinpoint the change vectors that are contributing to issues. For example, automatically breaking down user experience metrics by different dimensions and subpopulations, and then surfacing that data directly to our on-callers so that it's easier for them to triage issues and eventually mitigate them. Furthermore, the product we're responsible for is always evolving every single day, which creates potential for maintenance costs and decay of the metrics we've added. So as we've continued to iterate, we've actually started spending a lot of effort working on automated tools that can detect when the metrics that are integrated into the defense in depth framework have either gone stale or are experiencing another kind of anomaly. With these technologies, we aim to keep a high signal-to-noise ratio of alerts and prevent pager fatigue. So it's been quite an honor to talk about product reliability, and we would be very happy to answer any questions.